So in AP Physics 1, we covered a unit called simple harmonic motion, sound, and waves. And simple harmonic motion, remember, is whenever a particle is repeating a path. So it applied to pendulums, mass spring systems, things moving in a circle, and then also waves. So we spent a good amount of time talking about what are mechanical waves. And mechanical waves are waves that need a medium in order to travel through, and sound specifically is one kind of wave. So sound was a longitudinal wave or a compressional wave where we have the particles of whatever the material or the medium is moving parallel to the wave travel. So if we look at this wave going left to right across the screen, that means the particles are going to be moving horizontally in order to transfer the energy through the material to propagate the wave within that material. Right? We also looked at transverse waves, and transverse waves can also move through a medium, but we talked about the fact that we will also look into another type of transverse wave, which is a light wave. So that's the type of waves we're going to be looking at in this unit are all transverse waves. And in terms of mechanical transverse waves, we define it as the particles are moving perpendicular to the wave travel. So if we were to look at this first example here, you see this blue particle, it's moving up and down, so it's moving vertically within the screen, but you see the wave move horizontally across this screen. So this is an example of a transverse mechanical wave that requires a medium. But light waves don't require a medium, so they can travel through the vacuum of space, and they actually behave a little bit differently when they do enter into different mediums like air or glass or water, which we'll go into detail about. But they are a series of light waves are electromagnetic waves, and they're a series of oscillating electric and magnetic fields. So they have this transverse shape to them. So we see in this plane, we have an electric field, and then perpendicular to it in the other plane, we have a magnetic field, and we can see the wavelength being this distance here, but again, we'll go more into detail about that later, right? So the reason why I have the particles in quotes here is because now we're going to be dealing with transverse waves that there is no particle really, because there is no transfer of energy through a medium. It is just the movement of energy itself. All right, so all waves and anything that's undergoing any sort of harmonic motion is going to have a frequency and a period. So the frequency is the number of waves that pass a certain point in a given amount of time, and the unit is in hertz or 1/seconds or seconds to the -1. And then the period is the inverse of that, and it is the time that it takes for one wave to pass a certain point, and that unit is in seconds. So again, we're going to have both of these concepts popping up again in terms of electromagnetic waves. So we can see here that F is 1 over the period, or period is 1 over the frequency. All right, so let's look at the different wave parts, because this is going to apply to electromagnetic waves as well. So a wavelength is the distance between crests and troughs, and the unit is in meters. It is also the length of one wave cycle. So one wave cycle is going up, coming back down, and then returning to where we started. So one full wavelength would be the distance of one wave cycle. The distance from one crest to one crest, or one trough to one trough, should be the same as the length of one wave cycle in meters. So the crest is the tip of the wave, and then the trough is the base of the wave, and then the red line there represents what would be the wavelength. Then we have the idea of amplitude. So amplitude is really the height of the wave, and it's the height of the wave above like a base, like a rest position here. So amplitude is this rest position to the tip of the crest, or this rest position to the base of the trough. And so both of these, we can see that this has a greater amplitude than this. And in terms of sound, we discussed how amplitude had to do with energy, and energy had to do with loudness in terms of sound. And when we relate it to light, we'll see that amplitude actually does also correlate with energy, but also isn't loudness, but it is the brightness of the wave. So they have a specific velocity that they travel based on the medium, right, when we're discussing mechanical waves. But electromagnetic waves don't require medium. We will see that there is a constant speed as it travels in the vacuum of space, but then as it enters into different materials, it tends to slow down. But there will still also be a velocity for a light wave. The velocity for the speed of sound in air at like room temperature was roughly 343 meters per second, and we'll see that light is a lot greater than that. So the wave equation relates the wavelength and the frequency to the velocity. So velocity is equal to wavelength times frequency, so they're inversely proportional to one another. So as the wavelength increases, the frequency decreases, or as the frequency increases, the wavelength decreases. All right, so there's some different characteristics of waves that I want to go back and sort of remind you of that are going to come back now that we're talking about optics. Not all of the properties we discussed in the sound unit will come back, but these four are important. So when a wave encounters a boundary, it's going to do one or two things as it interacts with that boundary. It is going to either transmit energy through the boundary, which is called transmission, or it is going to allow the energy to bounce back into whatever medium it came from, right? And that is called reflection. So we will both see transmission and reflection when we are observing the wave properties of light, right? So here, if we recall, as a wave moves through a boundary, so this would be my boundary here, right? You can just visually see that each one of these springs has a different medium. Some of that is going to be transmitted into this new medium here, and some is actually going to reflect back into the previous medium, right? So you can see that some of the energy went over here, and some of the energy went over here. And we can see that the energy is conserved just by the height of the waves. So this, you can see this amplitude, and then you can see this amplitude and this amplitude together would equal the initial amplitude that we had. So we have some of it moving or transmitting and some reflecting. And notice, like, this boundary is not fixed. And so when there's reflection off a non-fixed boundary, then we have the wave that reflects back in remains upright. And that will become important as we talk about reflection of light waves too. All right, so for a fixed end boundary, it's a little bit different. So as we have a wave that's coming along here, it's going to encounter this fixed end boundary, and then it's going to reflect off. And as it reflects off, we can see that it is a little bit shorter than it was before, so there was some energy transmitted into this new medium, not quite as much. But as it reflects off, we also see that it inverts upside down. So remember that as light waves or any type of wave reflects off a non-fixed boundary, they come back into the medium right side up. When they bounce off a fixed boundary, they invert themselves as they bounce off. All right, wave diffraction is when a wave will bend around a boundary. So we use this concept of the barrier islands. So you have a boundary here and here, and as this wave comes in like this, along these edges, the wave ends up bending, and so we end up with this change of the wave front over here. And we will observe that also in terms of electromagnetic waves. Right? And then lastly, we have wave interference. So the idea of superposition just means that waves can travel through each other without disrupting each other. So if you have two light waves coming at each other, they can go past one another and then keep moving along. So if we see this idea of interference, constructive interference is you've got two waves, they're coming at each other, they encounter each other, and when their wavelengths come together, they will constructively interfere, and their amplitudes are actually going to add together, right? But then they continue along, and you can see that neither one of these has been disrupted by passing through each other. That's what superposition is, right? So this is an example of constructive interference. So in this case, you would see some bright spots, or you would hear some loud noise. Whereas if we were doing destructive interference, if the waves come along and they encounter each other, eventually they would cancel out, right? So if they were overlapping each other, the red is sort of the resultant line for that wave, and they would cancel each other out, but then continue along in their way and not be disrupted. So destructive interference for sound, we talked about how it would be dampened or the sound would be muted, whereas for light, we'll see that it will translate to dark spots. So hopefully this sort of brings back some of those concepts from waves, and you can use them now and start to apply them to as we move into our unit on optics.